about UDP segment header, and we said these are the fields in the segment header as far as UDP is concerned. Source port number, then we have 16 bits for destination port number. Then we have the length, which includes the length of the header. Header is of uh, 8 bytes. Okay, and checksum as well, right? So the payload field contains whatever is coming from the upper layer. Okay, so this is the UDP segment. So whatever is coming from the upper layer will be encapsulated in the payload field. And if we expand the headers, so these are the fields that will come across. Okay, source port number, destination port number, length, and checksum. Okay, so we also try to look at a UDP segment by capturing traffic using Wireshark. So we found out that these are the exact fields there as well. Okay. Uh, so we need to talk about checksum. Uh, Checksum is used for error detection and uh, basically for error detection, so that the receiver can identify that there has been an error while the bits were transmitting from one machine to the other machine, right? So how this error detection work? Let's try to have a look at it. So yes, we know that we may come across errors while the bits are being transmitted. Means some of the bits may get changed. Okay. So, for example, if this is data that is being sent, there is quite a possibility because of the attenuation or because of the noise or other, transmission factors or factors that can affect the transmission. This one can change into zero, right? And then maybe the zero can change into one as well. Okay, so it's very important that at the receiver, we are able to identify that if it is the same data that was transmitted by the sender or not, right? So if we talk about any error detection mechanism, um, what we do is we take the data bits, right? For example, these are the data bits. We take the data bits, and using the data bits, we calculate some redundant bits known as EDC bits, error detection and correction bits. Right. So the uh, goal of any error detection mechanism or correction mechanism for that matter is to calculate redundant bits, extra bits, right? And we will use these extra bits uh, to to identify whether there is an error or not. Okay, at the destination. So how many number of bits will be there in the this EDC portion, right? It depends on the error detection mechanism, right? So if I'm using, there are different error detection mechanisms such as we have listed these before as well, right? So for example, parity checking. Then we have checksum that we'll discuss today, right? Checksum is used by TCP, UDP, and IP as well, right? So this checksum is used by UDP, TCP, and also at the network layer by IP as well. Okay, and then cyclic redundancy check (CRC). Okay, so CRC is used by most of the mechanisms at the data link layer. For example, Wi-Fi, Ethernet. Okay, etc. etc. Okay, so the job of these error detection techniques are to calculate extra bits, redundant bits, and there are different ways in which we calculate redundant bits. Right. Today we'll learn how we can calculate these EDC bits, error detection and correction bits using checksum. Okay, so simple. In checksum, what we do is that if the sender has to transmit two numbers, say number one and number two, uh, is five, and five for number two is six. And then it also calculates its section, which is 11, and the receiver at the other end also does the same, right? And if there is a difference in uh, if there is a difference in the checksum, this means there is, or in the sum, this means there is an error. But let's try to understand this with the help of this example. So let me first of all explain this to you with a very simple example. Then we'll have a look at it, right? So, for example, these are my data bits, and I need to calculate error detection and correction bits. So what I'll do is I will divide my data into two equal chunks. We usually divide it into 16 bits chunks, but I have at the moment total 8 bits, so I will divide it into two chunks. One, 100, and the second chunk is 0011, right? So what I'll do is I'll add them together. I will calculate the sum. Okay, yes, no. So, and then I will take one's complement, right? Means all zeros, right? And this will become my checksum. Okay. So now, when the sender has to transmit the data, sender will send these data bits and also the redundant bits that we have just calculated. And okay, so these are my redundant bits or checksum in this case. Okay, so now what the receiver does is the receiver takes the receives the data plus the extra or redundant bits. Okay, so receiver again divides these data and EDC bits into chunks of 4 bits. So 11000011 and EDC bits 0000 and take its sum. Okay, so if we add them together, so this is its sum. Yes, no, and the receiver also then again take its mass complement to calculate checksum, and then this will come out to be. If we receive all zeros and if we after doing all this process, if we have all zeros, this means no errors. Okay, this means no errors. Okay, right? But if we have any bit other than 0, right, after taking one's complement, this means this data is erroneous and needs to be retransmitted. Okay, clear?
Yes, sir.
Right. So now, and remember, every error detection and correction mechanism has some challenges or shortcomings. Okay, the same is true with checksum as well. So let's take another example. Let's say I have to transmit two 16-bit integers, right? So what I'll do is at the center side, first of all, I will calculate a sum, and if I try to calculate sum, in this case, for example, for this data set, these two integers, I will get a carry. So what you will do with this carry. Yes.
Add it back to the number.
Yeah, it will be wrap around, right? So, and then we'll again calculate the sum. So now we have calculated the sum, and in order to calculate my EDC bits at the center, what I have to do is I need to take one's complement, right? So this will become my checksum, right? Now this is my checksum, okay? Or I can say my EDC bits, error detection and correction bits. Okay, and now on the other side, what the receiver will do is will take these three values, and the EDC bits, and we'll add them together and we'll calculate whether there is an error or not. Okay, clear? So when receiver adds all these three 16-bit values, integers, right? So receiver will get all ones. For example, if there is no error and if we take its checksum, it will have all zeros, right, indicating that there is no error. Okay. But if we talk about the shortcoming of this mechanism, checksum, it has weak protection in a sense that if two bits at the same position are changed into um, into integers, the consecutive in consecutive, uh, integers, this cannot be identified as an error. Okay, it fails to identify this error. For example, let's assume that these bits have changed from uh, you know 1 to 0, and this has changed from 0 to 1, 1 to 0, and 0 to 1, right? So bits at the same position into you know uh, into integers have changed, right? And you see this results at, this makes no difference in the sum remains the same, right? So if I add 1 and 0, the sum is 1. 0 and 1, the sum is 1, right? So such an error will not be detected uh, at the receiver, right? Do we have an error in this case or not? Yes, we do have error, right? But this error cannot be will not be detected by the, so this is a shortcoming. I mean, the cases where the bits at the consecutive bits that, in two chunks at the similar positions are changed, the receiver won't be able to detect this. Okay, and this is because we'll explore in detail at the data link layer. This is because of the bulk error, right? Such an error is known as bulk error. Okay, bulk error means more than one bits have changed, not in terms of rows, but it has changed in terms of, you know columns as well, right? So we have more than one bits have changed. Whenever uh, error changes more than one bit, so more than one bits are changed, this is known as bulk error, right? So this weakness is because of bulk error, and this is a special case in bulk error where the bits at the same position in two chunks or integers have changed. Okay, am I clear?
Yes, sir.
Okay, so so if we try to summarize our discussion on UDP, so we discussed that it's no frills protocol. It's a simple protocol, right? It does not add anything on top of the best effort service delivery provided by Internet Protocol. And by saying so, this means segments may get lost or can arrive at out of order at the destination, right? So it's just the best effort. We hope for the best, and we send and hope for the best means it will be delivered on the other side, right? But it has a lot of plus points. Advantages means it does not need to establish a connection. So this means we do not need RTTs to establish connection and all that, and it can still function if the network service is compromised, because will keep on sending. The application nature of the application is such that it does not mind data losses, right? It helps with reliability, means we have checksum with all its shortcomings, right? And most importantly, modern uh, or the recent HTTP standards are based on UDP, right? Yes, we need reliability, we need congestion control, and we implement this as a part of Quick. Okay. All right. So now we need to move towards TCP, but before we jump into TCP, because TCP is connection oriented and TCP is what? TCP is reliable. Okay. So we need to understand principles of reliable data transfer, and we will try to understand the principles of reliable data transfer by developing a reliable data transfer protocol, right? No, and then we'll see what I mean, how the reliable data transfer protocol in terms of TCP's reliable data transfer mechanism works. Okay, so first of all, let's try to understand the principles of reliable data transfer. Okay, so when we say that the data is sent to the other side reliably, this means we are making this abstraction that the underlying channel is reliable, right? So reliability gives us this reliable service abstraction, right? Considering that this underlying channel is reliable, means it can introduce no errors, right? Packets cannot get lost, right? And there is no chance of reordering, etc., etc., right? Okay, so well, this is not true, right? In fact, all the problem, or majority of, rather I should say, the problems are because of the underlying channel, because the underlying channel is not reliable. But if we think of a reliable data transfer mechanism, this gives me a reliable service abstraction as if the underlying channel is reliable. In fact, the underlying channel is not it is unreliable. So that's why I need to have a reliable data transfer protocol, right? Both obviously on the sender and the receiver side, okay, so that I can provide this reliable service abstraction that the data is sent reliably to the other end. Okay, yes, that we know that whenever a machine needs to send the data, the sending process pass this data through socket to the transport layer, right? And then the transport layer forwards it to the network layer, and then it is sent across the network to the other end. Okay, so this means at the transport layer, we need to introduce a mechanism ensuring or providing this reliable service abstraction. Okay, and this becomes, you know, this becomes more important or desired, right? Essential when, especially, we have no idea about the the receiver state. Okay, so I will come back to this point. This is a very, very important point. But so this means we have no idea about the sender service does not know, sender receiver does not know each other's state, right? The sender receiver do not know each other's state. They have no idea that the message was received or not, right? Until unless explicitly told, right? So until or unless sender receiver are sending some sort of, communicating with each other. I mean, receiver is sending acknowledgement. The sender won't be able to identify the packet is received on the other side or not. Okay, but let me come back to this point. So the complexity of this will keep on discussing again and again. Okay, the complexity of this reliable transfer protocol, reliable data transfer protocol depends upon the challenges posed by unreliable channel, or means the characteristics of unreliable channel. If the unreliable channel is only introducing or flipping bits, for example, this is one challenge. But if I am also losing packets, or packets are being reordered, okay, while during transmission, then the complexity of reliable data transfer protocol increases. Okay, how complex the reliable data transfer protocol, it depends upon the underlying unreliable channel and its characteristics. Okay, we'll see that. So before we jump into developing reliable data transfer protocol, right? So what we'll do is we'll try to develop different versions of reliable data transfer protocol (RTT), right? And by assuming the or introducing the different characteristics of underlying channel, unreliable channel, introducing complexity in the reliable data transfer protocol as well. Okay, so for that, let's for our convenience introduce some interfaces that we'll use in our example. Okay, so first of all, if the sender side has to send data, provide this reliable service abstraction. So I'm just introducing these four methods that I will refer to again and again for the understanding of this reliable data transfer mechanism. The first one is reliable data send. So whenever there is a call from above, means an application process wants to send data, right? The data will be passed to this method so that it can be delivered to the transporter. Okay, so this method data will be passed to this method, right? So this method is called, when we'll call this method when we have to forward data to from the upper layer, means the application layer, to transport layer. Okay, and then the transport layer forwards needs to hand over this data to the uh, network layer or on the unreliable channel. For that, I will be using this second. So this is the first method here. I will be using the second method, which is UTT, unreliable data transfer underscore send. Okay, this is called by reliable data transfer protocol RTD to transfer packet over the unreliable channel. Okay, so whenever the data is there's a call from the application, the data is passed from the application process to the transport layer. Will use this method, and then from the transport layer to the unreliable data transfer, will use this method. Right? Okay, and obviously we know this. We have covered encapsulation. We'll be adding headers as well. Okay, and on the receiver side, I have this reliable data um receive. Okay, so this is called when a packet arrives at the receiver. Okay, and then we extract the packet. We perform some calculations. It depends on the variant of reliable data transfer, and then we need to forward this data to the upper layer, application layer, using this method, which is deliver data underscore data. Okay, so I'll be using these for methods to explain the different variants of reliable data transfer protocol. Okay, so let me move on. So, in order to explain or understand the principles of reliable data transfer mechanism, I'll take help of a finite state machine, right? So we'll use finite state machine to specify the events and the actions that that take place while we are sending and receiving data. Okay, so finite state machine is very extensively used if we talk about automata or compiler, for example. Okay, or advanced automata, for example. A machine can be represented as a computer can be represented as a finite machine. Okay, right? So whenever I talk about representing uh, a process in terms of or in terms of finite state machine, so we have different states, and then I can do a transition from one state to the other state. Okay, so I can do a transition from the one state to the other state if an event takes place, and we take some actions as well. So if there is an event causing this what change in the state from state 1 to the state 2, right? And we also take action on the state transition. So we'll always have some event, uh, uh, and in result of this event we have to take some actions. Okay, causing this change in the state, right? For example, this from state 1 to the state 2. Okay, so we'll take the help of this finite state machine to understand this. Okay, let's talk about the first variant. Okay, reliable data transfer 1.0. So this is a very simple reliable data mechanism where the underlying channel is perfectly reliable. I mean, the underlying unreliable channel is that we are assuming is at the moment is not introducing any bit errors, and no packet losses are observed. Right. So this seems a very ideal, perfect underlying channel, right, where there are no errors and no loss of packets. Okay, so if I want to represent or I want to develop a reliable data transfer protocol mechanism for such a channel, right? So it's very simple. I need one state at the sender and one state at the receiver to represent this. For example, at the sender, I have a state which says wait for call from above. The state is wait for call from above means when an application process, excuse me, when an application process has to send something. So what it will do is, right, it will call, forward this back, um, forward the data to the transporter using reliable data underscore send. Okay, right. So if there is a call, so we take this transition. This is our reflexive recursive sort of transition. If there is a call, the data from the application layer is passed to this reliable data underscore send. So this is the event, and so this is the event that takes place. Okay, let me write it clearly. And remember, for a state to be successful or for a transition to another state, or maybe to another state, or maybe the same state, the event should, in case of an event, we also need to say take some actions. So the event is what? Reliable data underscore send. When an application process has to send some data is passed, or this event is called. Okay, method is called. This event takes place, and what are the actions that we need to perform? Okay, we'll take this data and make a packet, right? And now this packet needs to be passed to, remember, unreliable data underscore send for onwards transmission to unreliable channel. And on this event and taking these action, I will do a transition back to this state, and I will again wait for a call from above for the next transmission of the next uh, uh, data chunk. Okay. Similarly, at the receiver side, one state is enough, and that state is wait for call from below. I mean, we receive, whenever we receive, whenever we receive data. So, so this is an event that takes place, right? So we receive packet, and this is called, this method is called, right, which is reliable data underscore receive. And on this event, there are certain actions that we need to take. That is, we'll take the data, we'll extract, you know, the data from the packet, and we'll pass it to the deliver underscore data, which will, pass data to the application process at the destination, right? And by doing so, I'll make a transition back to the state and will wait for more incoming packets. It's a very simple representation. Yes, no. So this is a very simple, reliable transfer mechanism where there are no errors, no loss of data, and this results into a simple, reliable data transfer mechanism. Okay, but actual unreliable channel can introduce, a lot of problems. Let's try to introduce one by one and optimize or change our reliable data transfer mechanism protocol, right? So let's say now we have a channel with bit errors, right? So bits can get flipped on its on their way to destination, right? So how do we recover? How we can identify a bit error bits, but EDC bits are there for even parity checking for all the error detection mechanism. But at the moment, at the transport layer, we can make use of checksum, okay, internet checksum to detect error, right? How to recover from error? How do humans recover from errors during conversation? Excuse me, can you please say it again? Repeat. Okay. There are two ways using which we can recover from an error in our, in our conversation, right? So one is that we can ask the other person to please say it again, repeat. Huh? And the other way is to, I will try to resolve the error myself. Okay. I will try. I'll keep on thinking, okay, what the other person was saying to me, and then it will try to resolve that with myself. Okay. So in networks, we can also follow the both technique, but at the moment, let's say that in case of an error that we have detected using checksum, we can ask the sender to, okay, right? Same as in during our conversation with an error, we can ask the other person to repeat it. Okay, so uh, so this new error detection mechanism, this new reliable data transfer mechanism is say reliable data transfer 2.0, right? And now the characteristic that we are introducing in the underlying channel is that it can introduce errors, right? This it's an unreliable channel with obviously bit errors. Okay, so in case of for the recovery, what we'll be doing is how do we know that there is no error or there is an error, right? For that we use two types of acknowledgments, right? One is acknowledgement. So if a receiver receives a packet and there is no error, doing checksum, it finds that there is no error, so receiver will send an acknowledgement. Okay, so acknowledgement using this act, receiver explicitly tells sender that the packet received okay, I mean there is no error. But what if there is an error? So now receiver can send negative acknowledgement, right? So receiver can sending negative acknowledgement receiver can explicitly tell the sender that the packet had errors, so that the packet can be retransmitted. And later on, we will see that we can get rid of negative acknowledgement, and one acknowledgement is not enough. But just for our understanding, we will start with a very basic way how to deal with error. So now that we have already decided that in case of NAC, which tells the sender that receiver received the packet with some error, right? So the sender will be retransmitting, okay, the same packet. And at the moment, the mechanism that we are using for this, sending the packet and receiving responses is stop and wait, right? So we have already briefly talked about stop and wait, if you remember, right? If you recall, in stop and we said, okay, fine, if this is machine A and then we have another machine B, and this is the timeline here. So in stop and wait, what we do is we transmit one segment of packet and then we wait for acknowledgement, right? Or say in this case, negative acknowledgement, okay? And upon receiving acknowledgement and negative acknowledgement, we can send, will proceed sending the next segment, okay? So that's why we call it what? Stop and wait. We send transfer one segment and then wait for acknowledgement, and this in this case a negative acknowledgement, right? And then only the next segment or this segment maybe, for example, if we receive an acknowledgement which indicates what? If the response from machine B is acknowledgement, it indicates
No error.
no
The
errors.
package is safe.
Yeah, but yeah, there's no error. So this means I can proceed by sending segment number two, which is the next segment. Okay, but what if I receive a response from machine B and it's an ACK?
It means there is an error.
So this means an error, and error means what?
Retransmission or stop and wait.
Yeah, you're right. So in this case, we'll be retransmitting segment number one. Okay. Yes, no? Yes. So, but
Yes, sir.
yeah, but it's important for us to understand that in stop and wait, we send one segment and wait for the acknowledgement or negative acknowledgement in this case, and then we send the next segment or retransmit the previous segment depending upon the nature of the acknowledgement. Okay. हमने पहले भी कवर किया हुआ है stop and wait, ARQ, automatic repeat request, go back and automatic repeat requests, selective repeat, automatic repeat request, if you can recall. Anyways, so now to handle the errors, I will introduce another state at the center, right? So in the center side, I will introduce another state in RTD 2.0 so that I can take care of acknowledgements or the negative acknowledgement. So this state is the same. Wait for call from above. And now, after sending a packet, I will make a transition to this state. Mean I'll be waiting for either acknowledgements or negative acknowledgements. So, for example, if there is a call from above, right, and an event will take place, and the event is this reliable RTD underscore send is called by the application process, or data is forwarded to this is passed on to this method, and in in response to this event, we need to take some actions or actions. Yeah, it's important to understand. So we need to make packet. So the data is passed in order to make packet, but this is new. Now we also need to calculate what checksum. Remember, it was not there previously, right? In the previous version, um, we only had passed data to this make packet uh, method, right? Yes, no. But now we also need to calculate what EDC bits by using checksum. Using checksum, we need to calculate um, EDC bits. Yes, no. And then we have packet and the data which is passed to this unreliable data sent so that it can be sent over an unreliable channel. And then we make a transition to this state where we wait for either acknowledgement or negative acknowledgement from the receiver side. ये बात आपको समझ आई?
Yes, sir.
See, it was checksum was not there because we were not in reliable data transfer 1.0. We were not expecting any errors. Okay, we're assuming it's a channel where there are no errors. Anyways, so now if we in an ideal scenario, if being in this state, which is wait for acknowledgement and or negative acknowledgement, if this is the event is that it receives a packet and packet is
And act segment.
yeah is an ACK.
Correct.
An ACK indicates what? No errors. Okay, so so I will make a transition from this state to back to the state, which is wait for call from above. Okay, means I can proceed in stop and wait. I can go and I can transmit the next segment. Okay, and I don't need to take any action, right? So the no action is required. It will make a transition from back to this wait for a call from above. So remember, so so when we have to send data, say this is segment number one, right? So we make a transition from this state to this state, and we wait for an acknowledgement and a negative acknowledgement. And if I receive a response, a packet, and the packet is what? Acknowledgement, right? So this will make me to move to back to the state, which is wait for call from above. This means I can proceed sending the next segment in line. Okay. But what if it is negative acknowledgement? What if this response is what if this response is uh, NAC? I receive a packet and the packet is NAC. What will happen in this case? Should I be
We
sending?
transfer the first.
Yeah, should I be sending the next segment? No. Should I be making this transition from this state back to the wait for call from above state? No. Right? Yes, no?
Yes, sir.
Yes. So if this is the case, if sender receives a packet and packet is what? NAC, right? This means I need to resend the packet, okay, which is segment number one in this case, okay. So the action is we will resend the packet, okay, and we'll go back to the state where we'll wait for either acknowledgement or negative acknowledgement. We will not make a transition back to the state until we receive what? A packet, and the packet is happen at the receiver side. Okay, let's have a look at the actions at the receiver. I mean, what the receiver will do. One state is enough at the receiver to handle, you know, this change or this introduction of a characteristic in underlying channel. So, so we wait a packet. The event is receiver receives the packet, and the packet is corrupt. Process this, segment and will not pass data to application layer, but in fact it will send a negative acknowledgement to the sender and will go back to this. Will make a transition back to the state which is wait for call from below. Okay, what can be the other event? That we have received a packet and the packet is not corrupt. Okay, so the event can also be that it has received a packet and the packet is not corrupt. If the packet is not corrupt, these are the actions that will take or the receiver will take. It will extract the packet, okay, will and forward the data to upper layer using this deliver underscore data method, right? And will send what? Sender, okay, and sender upon receiving acknowledgement can make a transition to the state wait for call from above. Clear? So so let's try to navigate through the uh, uh, through the different events and actions, right? So this is an operation in a reliable data transfer 2.0 with no errors. Okay, so what will happen is that there is a call from above, right? So this event takes place. The data is passed from the application layer to this reliable underscore send data, and these are the actions that we take. We take the data and calculate the checksum and send this packet to the receiver, and uh, after sending the packet, we'll make a transition to this state, which is wait for acknowledgement or and negative acknowledgement. And on the receiver side, the event is what? Remember, the operation is with no errors. The receiver receives the data, right, and a packet, and the packet is not corrupt. Okay, so the data will be extracted, will be passed to the application layer, and receiver will send an acknowledgement to the sender, right? So this receiver sends an acknowledgement to sender, right? So upon receiving acknowledgement, I mean, this is the event that takes place. The sender receives a packet and it is an acknowledgement. So no action is needed. So it makes a transition back to the state wait for call from above. Okay, so let's assume now the scenario is that certain errors or error has been introduced or packet is corrupted. So in this case, again, there is a call from above at the receiver side. These are the events. This is the event that will take place. I mean, will the following actions will perform this action. Will calculate the checksum and then we'll forward the packet to the unreliable data underscore send. And then after sending, we'll make a transition to wait for ACK or NAC. And on the receiver side, what is the event that is taking place? Receiver receives a packet and the packet is obviously, we're assuming the packet is corrupt. And in this case, receiver will send a negative acknowledgement and make a transition back to this state. Okay. So when we receive a negative acknowledgement, what will happen at the sender side? Sender will resend the packet and will transition back to the state wait for ACK or NAC, right? So now the packet is resent, okay, and we make this state. And now let's assume this time at the receiver, the event is it receives a packet and the packet is not corrupt, right? Or these are the actions. The packet will be forwarded. There will be forwarded to the application layer. And yes, most importantly, receiver will send what? An acknowledgement, right? So now this is the event that takes place for this transition uh, uh, from wait for act or nag to wait for call from above. Is it clear?
Yes, sir.
Okay. So now, but there is one thing that we have not, really considered while developing this RTD 2.0. We have talked about, yes, when we send this packet, right, the packet can be erroneous, but what about these acts or nags, right? What about the acknowledgement or the negative acknowledgement that is being sent by, right? So do they have, a protection from some sort of protection uh, errors, right? I mean, the bits cannot get changed in NAC or ACK. No, right? So there is a possibility, right? If we have uh, a channel where the bits can get changed, this is even true for NAC or NAC, right? But at the moment, we are only talking about that there is an error in data packet, right? What I want to say is, if A sends a packet, say one, and B sends acknowledgement, and what if this acknowledgement is garbled, is corrupted, right? Will A B understand what happens at B? No, right? If this acknowledgement or negative acknowledgement is garbled, A will have no idea what B is saying. Okay, are you getting my point? So
Yes, sir.
maybe A ends up sending, if A is unable to understand what the response is saying because it is garbled, it is corrupted, then maybe A will end up sending what? So
Next
it's,
segment.
yeah, no, 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 the same thing, because A is unable to understand it's what it is, right? Okay, but
Yes, sir.
what is happening at B? This is also important. What will happen at B? B will receive a duplicate packet, right? Yes, no. B has already received one. Yes, no. B will again receive and process a duplicate packet. Yes, no.
Yes, sir.
Yeah. So we need to understand the problem first, right? The problem is that if acknowledgement or negative acknowledgement is corrupted or is garbled, for example, change, A will not be able to understand the response, right? And A will, what A will do? A will say, ends up sending, A ends up sending the same packet, which is packet number one, for which we are waiting for acknowledgement or negative acknowledgement, and this will result in the processing of a duplicate packet at machine B. Okay, so these are the flaws that we need to, understand first, and then, we need to find a solution by changing reliable data transfer protocol 2.0. So what happens if acknowledgement and negative acknowledgement is corrupted, is garbled? So sender does not know what happened at the receiver. It can, if it, retransmit, this will cause duplicate, uh, packet processing at the receiver. So what we should be doing? Number one, we also need to calculate a checksum for acknowledgement and negative acknowledgement. And in order to avoid the processing of duplicate packets at the receiver, we need to add a sequence number with the packet, so that the receiver can handle duplicate packets by discarding a duplicate packet if it has already processed one. Okay, so let's try to understand. So I will explain it with the help of an example. So now, at the center, instead of two, I need four states. And you know if I talk about stop and wait, remember, at the moment we are talking about, boliye, stop and wait, right? Yes, no. Yes, we know there are others
Yes,
as
sir.
well. There's a go back and ARQ. Then I will talk about these as well, right? But let us start with the, try to understand the reliable data transfer mechanism, focusing on simple representation, okay, or flow control mechanism. Okay, so what I'm saying is, if we talk about stop and wait, uh, we know that we can send one packet and we have to wait for acknowledgement, or in this case a negative acknowledgement, and then we can proceed sending the next segment, right? So if I have to uh, if I have to uh, if I have to note sequence numbers, two sequence numbers are enough, right? For example, I can send packet 0, and if I receive its acknowledgement, I can send packet 1, and again I can repeat it, right? So two sequence numbers are enough in stop and wait. Why? Because at any point in time, I can send one segment. I cannot send the next segment until I receive acknowledgement or negative acknowledgement for the previous segment. Okay, is this point clear? Because now I have to, I have to also mention the sequence number in packets as well, segments as well. So what I'm saying is, in stop and wait, since we have to send one segment and then wait acknowledgement, and then the we can proceed with the transmission of the next segment, two sequence numbers are enough. Do you agree?
Yes, sir.
Yes. And what the receiver can now do is, receiver maintains, say, a variable, and receiver keeps a record. Okay, what it has received and processed. Say receiver has received a segment number one. So it's okay. Let me say 0, and receiver has, it was correctly received, and receiver has sent its acknowledgement, and let's say the acknowledgement has is corrupted. Okay, if the acknowledgement is corrupt, what A will do? A will I mean, A won't be able to understand what we
Accept.
A won't be able to understand what we saying. A will retransmit,
First one.
yeah, segment number zero. But what will happen at the receiver? This is a duplicate at machine B. There was nothing wrong with the previous packet, right? Previous packet was received okay. There was no errors. Okay, B has already processed the packet and has generated the acknowledgement, right? But the acknowledgement has garbled, as it has been corrupted. Okay, A is unable to understand what happened at B. Okay, and now A in this case will retransmit a segment zero, but this is a duplicate at B. So what we will do, we will discard this packet, okay, and will again resend the acknowledgement. Okay. So now in this case, what we are doing, we are handing duplicates at with the introduction of sequence number. अगर आप समझ रहे हैं अच्छी तरह से, with the introduction of sequence numbers, B or destination in this case is able to handle duplicate packets. Then packet which is acknowledgement, but will also have checksum as well. And looking at this checksum, B A is able to identify that the acknowledgement has garbled, is corrupted, and that's why A is resending this segment number zero. Yes, no.
Yes, sir.
Okay, so let's move to, if you're clear about this, let's move to this finite state machine diagram to understand this. Okay, okay, now we are in state wait for call zero from above, right? And let's say this event occurs, the data is passed from uh, the application layer to the transport layer using this event or method. So this is the event we know we have to perform some action. We have to make a packet. Look what is different now. We do have data and checksum in the previous version, which was RTD 2.0. Yes, no.
Yes, sir.
Yes, but what is new here? What we are changing here at the sender side? We are also adding what? In addition to data and checksum, we are also adding a sequence number. The zero is what?
The sequence number.
Yeah, so now the packet having sequence number, obviously data and the checksum is sent to uh, on this unreliable channel, right, to the towards the destination, and we make a transition to wait for acknowledgement, a negative acknowledgement for zero, right? Now we are waiting for acknowledgement or negative acknowledgement for sequence packet having sequence number zero. Yes, no? Yes. And let's assume the sunny day scenario. Let that when we were waiting in the state, this event takes place. The sender receives a packet, and yeah. So now this is again a similar, event, right? If machine A receives a packet and packet is not corrupt and is acknowledgement, so we'll make a transition, no action is stated, and we make a transition to this state wait for call zero from above. This means if it receives a packet and the packet is acknowledgement and is not corrupt, then we can proceed sending the next sequence number zero. Okay. Yes, no.
Yes, sir.
Okay, but what about the abnormal events? What about if the it's an ACK or it's a NAC or ACK or NAC is corrupt? What about all those possibilities, right? So, okay, let's try to explore this. While we were waiting for ACK or NAC, let's assume this is the event uh, which takes place, right? The event is uh, we have received a packet and either the packet is corrupt or is negative acknowledgement, right? So okay, now we have received this acknowledgement, either it is corrupt or if it is not ACK, I have received a NAC. In this case, what I'll be doing, I need to resend the segment 0. Yes, no? दोबारा देखिए.
Yes, sir.
Now the event is that obviously we have received a packet, and if any one of these two condition is true, right? There's an R here. Either the packet is what? Corrupt. Does not matter if it is acknowledgement or negative acknowledgement. It's corrupt, right? This means I'm unable to understand what happened at the machine B. Or if it is NAC, I've received a packet and it is not corrupt, but it is a negative acknowledgement. The action is that we'll resend the packet and make a transition back to this state until we receive a packet which is not corrupt and is an acknowledgement. Okay?
Yes, sir.
Yeah. So, what about the other side? The similar event happens in this state when we are waiting for acknowledgement or negative acknowledgement for one. The sender receives a packet, and the packet is either corrupt or is a NAC. In this case, the packet needs to be resent and will make a transition back to the state. Wait for ACK or NAC, and only will make a transition back to wait for call 0 from above if we receive a packet and the packet is not corrupt and it is an acknowledgement. Yes, no.
Yes, sir.
Yeah.
Yes,
So
sir.
yeah. So uh, what about the operation at the receiver side? So now one state is not enough because we one state is for sequence number 0, another state has to be there for sequence number packet having sequence number 1, right? So wait for 0 from below, and then we have wait for 1 from below. So if we receive a packet, so this is the event that will result into this transition. देखिए, if a packet is received and packet is
Not
not corrupt and has sequence number 0. Now here, this is very important. So here this sequence number 0, yeah. So here the sequence number 0, handling sequence numbers will help the receiver to deal with duplicate packets, right? So if it receives a packet and it is not corrupted and the receiver was waiting for sequence number 0, it has sequence number 0, then these actions will take place. Okay? It will extract the data, forward the data to the upper layer, and it will make a packet which is acknowledgement, and this should also include what?
checksum.
Checksum, so that the sender can identify when it receives an acknowledgement or let's say negative acknowledgement, that whether it's corrupt or not, right? And then it sends the acknowledgement to the sender in this case and makes a transition to the next state, which is wait for 1 from below. Similarly, in a sunny day scenario, in a perfect, where there's no error, the same similar event will take place to make a transition from wait for 1 from below to wait from wait for 0 from below, right? So now, if in this state, I if a packet is received and the packet is not corrupt, and most importantly has sequence number 1, right? So now the packet will be data will be extracted and will be forwarded to the application layer and will generate an acknowledgement with checksum, and the acknowledgement will be sent to the other side, right? But what about the abnormal events, right? What if we are waiting for call 1 from below and this event happens? That is, we receive a packet and packet is corrupt. In case of a corrupt packet, we remember the receiver has to send is supposed to send a negative acknowledgement, right? So now we'll send what? We will not process such a data because it is corrupt, right? This packet is corrupt. We'll send NAC calculating checksum, and we'll send this NAC to the sender. Okay, what if we are waiting for one, but we have received another? What about this scenario? right? So 0 is received, it generates an acknowledgement, right? Say acknowledgement is garbled, and now it is expecting, it has already processed 0 and is expecting the next in the sequence, which is 1. Okay, but it receives 0, right? What will happen, right? So this is state that we're talking about. This is the event, right? So now the packet is received, packet is not corrupt, but it has what? Sequence number 0, but sequence packet having sequence number has already been received correctly. So in this case, what the receiver will do, पहले भी डिस्कस किया था, receiver will send an acknowledgement, will not process, will discard it, and will not uh, process it, right? And will send acknowledgement. So make an acknowledgement and checksum and send it to the sender. Okay. Yes. No. Similar
Yes, sir.
similar events, identical events will take place for this. The other state as well, which is wait 0 from below, right? For example, the event is that while we're in the state, we receive a packet, but packet is not corrupt, but it has sequence number 1. We are waiting for acknowledgement having sequence number 0. Okay. So in this case, what we'll do is we will again discard the packet, will not process it, and will generate what? An acknowledgement. Okay. And if the packet is received and is corrupt, for example, the acknowledgement is corrupt, so what will happen in this case, or sorry, packet is corrupt, in this case, the receiver will send negative acknowledgement along with checksum. Is it clear?
Yes, sir. Sir, I have a confusion.
जी
What is
प्लीज.
this waiting from below or waiting from above?
सॉरी, दोबारा सवाल पूछिए.
Sir, what is this waiting for zero from below and from above? Like, what is the difference between above and below?
Okay, so remember, at the receiver, at the sender side, this is our sender and this is our receiver. Okay, sender, receiver, and remember we introduces 4 interfaces, right? हमने कहा कि whenever the data is sent, we have RTT underscore send, right, at the receiver, which will pass data to the transport layer, and whenever transport layer needs to forward it to the network layer and onwards to this unreliable channel, right? For that, we will use UTD underscore send, okay? And here, whenever the data is received, right? So this is that we wait for call from below means whenever the data is received from the load layer using this method RTD receive, okay? And then we'll extract it and pass it to the upper layer using this method, uh, deliver underscore data, right? Okay. So waiting for call from below is that whenever we receive a packet from, so we are in this state where we always, expecting for a packet to be arrive. Okay. And from above means that here the packet will be forwarded to the transport layer from the application layer. Okay. Yes. No.
Okay, sir. Thank you.
No worries.
Yes, sir.
Yeah.
Can you repeat the above part?
Sorry. Call from
Can you repeat
yeah, yeah,
the
yeah, call from above.
above part?
Yeah, yeah, yeah. So this, in this case, this reliable data transfer mechanism is always waiting for a call from above means where the application layer will call this method to pass this data to the reliable transfer data mechanism, right? So on the sender
Okay.
side, it will wait for a call from the above means the application layer is calling this method interface that we have introduced to pass the data. And on the receiver side, this reliable data transfer is always waiting for the call from below means for the arriving packet at the receiver side. Okay. Am I clear?
Yes.
Please ask questions if you have any confusion. Do not hesitate. Okay.
Sir,
So
the 0 and 1 will ultimately keep increasing for a greater number of RTTs or not?
greater number of RTTs. I mean, what you want to say?
Sir, the 0 and 1, will it stay 0 and 1 for every RTT, or it will change like
It has
3,
nothing to
2,
do
3,
with
4, and so on?
RTT. So there's no discussion on RTT at the moment. Remember the mechanism we are referring to. At the moment, we are talking about stop and wait. Let me explain it again, right? And stop and wait ARQ, if you recall, is a mechanism where we send only one segment, and then we can only send the next segment if we receive its acknowledgement, right? So we can send one segment, say zero, and then we wait for the acknowledgement before proceeding to the next segment, which is one, right? So two sequence numbers are not enough here because I cannot send more than one segment without waiting for an acknowledgement. This will change. This will change if, for example, I talk about go backend, right? Now I can send n number of segments. If you recall, I can send n number of segments without waiting for an acknowledgement, and then I can have this cumulative acknowledgement as well. I can segment one, two, three, right? So in this case, I'll be maintaining more than one sequence numbers. Okay, two sequence numbers in this case because I can send more
Okay, sir.
segments
Thank you
without
so much.
waiting for an acknowledgement, right? Because at the moment, just for the sake of our understanding and getting clearly explaining this reliable data transfer mechanism, I'm using a simple mechanism which is stop and wait. Am I clear?
Yes, sir. Thank you.
Okay, no worries. Okay, so what we did in 2.1 is that we have added sequence numbers to the packet. Two sequence numbers अभी सवाल भी पूछा आपने are enough because we are dealing at the moment stop and wait, right? So we must check if acknowledgement and negative acknowledgement is corrupted. We have increased the states twice as many states in the previous because दो थी हमारे पास 2.0 में और एक थी हमारे पास receiver में in 2.0. In 2.1 we have four at the sender and we have two at, so we have increased the number of states as well, and this is because the complexity of the complexity has because of the characteristics of underlying channel, right? Okay, but what we can do is, as I discussed initially, that I can get rid of NAC. NAC is really, we can, still achieve the same functionality without explicitly using NAC, right? So we can implement same functionality of 2.0, but now we will use only acknowledgement. So negative acknowledgement is extra. इसके बगैर भी हम क्या कर सकते हैं? We can make this reliable data transfer mechanism work, right? So what we do is that instead of NAC, the receiver sends ACK for the last received. Okay. So it has, if we add, sequence numbers also with the acknowledgement, right? So this can solve our the purpose, right? Uh, we can implement the same functionality without using what? Using NAC, right? आइए जरा देखते हैं किस तरह से. So I'm only representing one or a half of finite state machine, right? Or a fragment of finite state machine at the center side, right? I'm representing it for wait for zero from below and wait for acknowledgement zero, right? From above, sorry. So similar events and actions will take place for wait for call one from above and wait for acknowledgement one. Okay. अब ये बात समझ आ गई. अगर हमें ये समझ आ गया, this fragment and the other fragment is the same. Okay. So see, let me try to identify where is the change. So so we have this event where there is a call from above for zero. So this is the same. We did the same for reliable data transfer 2.1. It has a sequence number, data plus will calculate the acknowledgement and the packet is sent using unreliable data underscore data sent. Yes, no. And then we make a transition to wait for ACK, right? And previously there was a wait for ACK and NAC for zero. Yes, no. But now we are trying to implement realizing the same functionality without implementing NAC. Now, if the event is, look at the normal event. If the event is that the sender receives a packet, and the packet is not corrupt, and is an acknowledgement for, जी बोलिए,
For zero.
for zero, right? If we receive an acknowledgement and this is for zero, then only we will make this transition. We'll make this transition to, the state which is wait for call zero, sorry, one, wait for call one from above. Okay, right. So look at this, event. The sender receives a packet, and either the packet is corrupt or it is acknowledgement, but it is acknowledgement for one, right? Where the sender was waiting for the acknowledgement for packet zero, it will retransmit the segment. Okay, either it's acknowledgement or not, but I'm also checking whether this acknowledgement is zero or one. If this acknowledgement is zero and the packet is not corrupt, I will make the transition to the state wait for call one from above. But if I receive a packet, or either the packet is corrupt or is an acknowledgement of some other segment number, right, I need to resend this packet. So this will essentially give me the same functionality of 2.1, but in this case, I'm not choosing any negative acknowledgement. Okay, let's for better understanding, let's have a look at the receiver side. It's a fragment uh, of final state machine at the receiver, right? So if this is the event at the receiver, right, the event is receiver receives a packet and the packet is not corrupt and has the sequence number one, right? And here the receiver was waiting for sequence number one from below. Okay, so which will extract the packet, the data will be delivered to the application layer, and then it generates an acknowledgement. Look at the difference here. The acknowledgement has what? Both these fields were there previously as well. So previously, uh, in this tab we have send packet equals to make underscore uh, packet acknowledgement and checksum. So what has changed here? Now the acknowledgement also needs to have
The frame number.
acknowledgement number, right? Needs to have a number. Okay, right? And after sending this acknowledgement, we'll go to this wait state. Receiver, if receiver, for example, if receiver, sorry, if receiver receives a packet and either the packet is corrupt or is having a sequence number other than what the receiver is receiving is waiting for, it was waiting for sequence number zero, but the receiver has received a packet with sequence number one, right? So what I'm saying is, what this says that receiver receives a packet, and let's say packet is not corrupt, but it has a sequence number one, right? And receiver is waiting for packet having sequence number zero. Okay, receiver is waiting for zero, or say it has already received one. Okay, so receiver sends a packet. What it is? Obviously, it is acknowledgement, right? But it will be acknowledgement for what? So let's move on. And now uh, uh, we need to introduce more, new characteristics and new assumption for this. We need to make new assumption for this underlying channel. And now this time around, we're talking about a channel, where errors are there, but we can also expect losses as well, right? the new assumption in the channel is that the underlying channel can also lose packets. Lose packets means any packet can get lost. I mean, maybe it can lose a data packet, or maybe it can lose acknowledgements as well. Okay, देखिए अभी तक हमने क्या कहा है 2.2 तक, right? It's a channel where uh, error is possible both in packet and original packet and the acknowledgement as well. Yes, no, yes, right? But now let us make a new assumption about the channel where the packets can get lost, right? A packet means we can lose either data or acknowledgements, right? Okay, so we do have, up till now, we do have checksums, sequence numbers, acknowledgements for the transmission, right? But this will not be helpful. Only these only will not be able to help us to address losses. I mean, data packet losses or acknowledgement losses. For that, we need also to add some other characteristics, right? So the question is, how do human handle uh, lost data? Okay, so yes, automatic repeat request. And what does this mean, automatic repeat request? That we start a timer, and if we do not receive a response before the expiry of the timer, the segment will be automatically retransmitted. So when I ask you a question, and if I do not receive a response, so you know what I do, I repeat my question again. Yes, no.
Yes, sir.
Yes, right. So this means we need to add a timer in our previous implementation so that we can handle losses, right? Uh, this also includes data and um, uh, acknowledgement as well, right? So the approach is to wait for a reasonable amount of time, and this is a very very important discussion, that how much time we should wait, but we'll not discuss this here. We'll have a separate discussion on this. Um, if we will wait for a reasonable amount of time, and if we do not receive a response, right, then we will retransmit the packet, assuming either right. There's no change here, and now. Um when we have this event, which is we want to send the data, we make a packet, right? This is the same. It should have a sequence number and checksum also, right? And we send the packet, and we also do what? Start a timer. So the addition is on this event, uh, taking other action. We are adding this action where we'll start a timer at the sender, and then we wait for acknowledgement 0, right? So yes, um, if it's a normal scenario where we were waiting for acknowledgement 0, the sender receives a packet and it is not corrupt and it is acknowledgement, right, of 0, right? Acknowledgement having sequence number 0. So now, instead of having no action and making a transition to this state, the action includes what? Sorry, the action includes what?
Stop timer.
Stop timer. Okay, so and again, there's a similar event here as well. While we were waiting for a call from above, uh, this is usual. This is a usual action, right? And but now we are also starting a timer, sending the next segment, and then we are waiting for acknowledgement 1. And these are the same. Uh, these are the same. Uh, same event and action, right? While we were waiting for Act 1. Okay, and then we'll make a transition to. So this is a normal implementation. Yes, no, yes. So I need a scenario. We send a packet, you know, we start a timer. Before the expiry of the timer, we receive a response, and the response is expected response. I mean, the acknowledgement 0, right? And then we make a transition from wait for act 02, wait for call 1 from above, and stop the timer, and then so on and so forth, right? But if we what if we are waiting for acknowledgement and we have this event? Okay, We are waiting for acknowledgement and timer goes off. The action is that
It will be sent again with the start timer.
will be sent the packet will be sent again and will also start the timer and will again wait for its acknowledgement. Okay. And what if we receive a packet and either the packet is corrupt or is acknowledgement but not the one that we are expecting? We are expecting acknowledgement zero, and let's say it's acknowledgement one. Again, we'll do what? We will
Retransfer.
retransfer.
Retransfer with the timer.
No, right? देखिए क्या होगा. आप देख रहे हैं इसमें इसने कुछ एक्शन नहीं है. लेट मी ट्राई टू एक्सप्लेन दिस. आप कह सही रहे हैं बट ज़रा क्लियरली हमें इसका सीक्वेंस देखना पड़ेगा क्या हो रही बात. So what this is telling me is that okay, I've received segment. Where it is? Yeah, I have sent segment number zero. I received an acknowledgement. Right? Either the acknowledgement is corrupt, okay, or it has number one. I mean, the acknowledgement is segment number one. I'm waiting for acknowledgement for the segment number zero. In this case, what is the action? Look at the action. What is the action? What is the action here?
You wait for acknowledgement zero.
Nothing, nothing. So this means I will not take an action. Why? Because
Timer is there.
your timer will expire and this packet will automatically be
Sent again.
resent. Okay. Is this point clear?
Yes, sir.
Yes, sir. Okay. So again, and what is this? This is very important. Uh, can any one of you explain this event and action?
So the packet is received.
And no action is taken.
Yes, no action is taken.
So now let me draw a scenario here for you, and then you try to explain it. So in this case, we are waiting for call from above, and then we have received a packet, but we are not taking any action. So we have received a packet, and this packet will obviously what will be? बोलिए.
Acknowledgement.
It will be acknowledgement, but this is such an acknowledgement on receiving, which we are not taking any action. What do you think? What is going on? Let me explain the. Let me complete this scenario, so that you can answer my question. Uh, so, so let's say it has transmitted packet number zero. It receives the acknowledgement for zero, right? At this point, okay, we are in we are in a state which is wait for call one from above, and it receives another packet. But on receiving this packet, obviously this packet is an acknowledgement. It takes no action and stay in this, and the sender stays in this state, which is wait for call for one from above.
It means the transmission is completed.
Sorry?
It means the transmission is completed. There are no more packets to send.
No, no. We are waiting more packets to be sent. But what is this? What is this acknowledgement on which we are not taking any action?
It will wait for the timer to
No, no, no,
expire.
no, no. We are
It
in
will
this.
wait for the timer to expire, sir.
No, no, no. We are in the same state. We have not sent the next segment. We are waiting for a call from above right? So that we can send the next segment. And we have already received acknowledgement, but we receive another acknowledgement on which we are not taking any action. And this acknowledgement is, I'm telling you, this acknowledgement is acknowledgement.
It could be a duplicate acknowledgement.
Yes, it is a duplicate acknowledgement. Okay. So in this case of a duplicate acknowledgement, I need not to do anything, right? I'll again make a transition back to this state where I'm waiting for the call to transfer the next packet. Am I clear?
Yes, sir.
Okay. So in similar events will, exceptional events will be there, or the events to handle exceptions will be there for wait for uh, act one, right? So if a timeout event while we are waiting for acknowledgement will set the time packet again and will packet one again and will start the timer, right? And if we you know receive a packet and this packet is either corrupt or is an acknowledgement for uh, some other sequence number. So we'll do nothing and we'll wait for the acknowledgement, right? This we have already covered. And again, in case of a duplicate acknowledgement, we need not to do any action. Take not we need not to take any action, right? Let's try to have a look at it from another perspective. खैर मैं आपको बताता रहा हूँ ये खुद ही draw करके. But let's see this reliable data transfer 3.0 in action. And the first scenario is where there are no losses. Okay, so see, we transmit one packet, which is packet number 0, and packet number 0 is received. In this case, the receiver will send acknowledgement 0. Acknowledgement 0 is received, and then we will transmit next segment, and then receive its acknowledgement, and so on and so forth. And you can see at the moment, because we are talking about stop and wait, the two sequence numbers are enough. Okay, so 0101, we are repeating these sequence numbers. Okay, and let's assume another scenario where we have packet losses. That is, we transmit a packet 0, we receive its acknowledgement, and then we proceed sending the next segment, right? What will happen in this case? After sending this packet, remember, we also need to start a timer, and then now we are waiting for the acknowledgement. Will we receive any acknowledgement in this case?
No,
No,
sir.
because the receiver has not received any packet in this case. So the timer goes off, right? Timer expires, and then we need to resend this packet number 1. Okay. Now the receiver receives packet 1, and it sends this acknowledgement, and so on and so forth. Okay. Yes. No.
Yes, sir.
Excellent. And let's assume a scenario where there's a loss, but in this case, acknowledgement has lost, right? So we have transmitted segment number 0, we receive this acknowledgement, then we send segment number 1. Segment number 1 is rightly received by the receiver, but this acknowledgement has lost. What will happen at the sender?
Timeout.
There will be a timeout and we'll be resending segment number 1. When we resend segment number 1, receiver will detect it as duplicate packet, will discard it, and will generate acknowledgement 1.
Yes, sir.
You can see sequence numbers in action here, because using the sequence number, the receiver is able to identify that it's a duplicate, and the duplicate in this case will be discarded, and we will again send acknowledgement 1. Okay, well, this is important, right? This is the case that we were talking about, a delayed or premature timeout or a delayed acknowledgement. Okay, remember where we made a transition back to wait for 1 from above or 0 from above, right? Taking no action, right? Do you remember that action, even an action? Okay, so let's assume that packet 0 is sent, packet 0 is acknowledgement 0 is received, then we send packet 1. This is important, right? And packet 1 is received, acknowledgement is on the way, but it's a delayed acknowledgement, right? It is what? Delayed acknowledgement. Or we may have this premature timeout. Okay, the timer is on the way, so the acknowledgement is on the way, and we have a timeout event. So what we'll do in this case? Packet 1 will be retransmitted. Okay, so packet 1 is retransmitted, and packet 1 obviously is a duplicate packet at the receiver. It will be detected and it will again send what? Acknowledgement 1. But what action will be taken on receiving this acknowledgement 1? We'll do a transition to wait for 0 from above, right? And if we receive another acknowledgement, which we'll do in this case, no action will be taken at the receiver, right? So if I go back quickly, yeah, so this is this action that we're talking about. Yeah. Okay, दोबारा देखिए शाबाश. So packet 1 is sent, acknowledgement received. Then we send packet, sorry, 0, acknowledgement 0 received, packet 1 is sent. But the acknowledgement is on the way, but it's a delayed acknowledgement, or maybe there's a premature timeout. Okay, so the timer goes off, and we will again retransmit this packet 1 again, and we'll transmit this packet 1 again, and now at the receiver, the duplicate will be detected, and receiver will resend acknowledgement 1, and we have here two acknowledgements, right? What we will do with this acknowledgement? Will take no action, right? Okay, yes, no, we'll ignore
Okay, sir.
this acknowledgement, right?
Yes, sir.
And we'll send the next packet, and then so on and so forth. Okay, right. So let's talk about, so what we have done so far is that we have tried to come up with reliable data transfer protocol by introducing different characteristics to this underlying channel, right, or making it, more complex, the reliable data transfer mechanism, by making different assumptions about the underlying channel, right? And it's time to evaluate the performance of this reliable data transfer, especially keeping this mechanism stop and wait in mind. Okay, so and we'll try to analyze the performance by calculating the utilization, right? That is the fraction of time the sender is busy sending the data. Okay, this will indicate that how efficient, I mean, how much percentage of the time the channel is being utilized for sending the data. Okay, so we'll calculate this utilization. So for this example, I'm assuming that I have a length of 1 gigabits per second, and the propagation delay is 15 milliseconds, and there are 8,000 bits in a packet. Okay, right? So if I have to do this calculation, I mean, I have to calculate this, transmission delay. So how I can calculate transmission delay?
Length
Remember,
of packets over transmission
remember the transmission
rate.
delay, the time to push the packet to the channel. हमने बहुत extensive इस पे discussion की हुई है, right? So this is the time that is required to push the packet onto this, onto the link. Yes, no, yes, right. And how we can calculate this, delay by dividing the length of the packet, or the size of the packet is divided by the uh, transmission rate, R. So the size of the packet is L, means is 8,000 bits, and the link is 1 gigabit. This is 1 into 10 raised to power 9 bits per second. So the transmission delay is 8 microseconds. Okay. So Uh, look at this. Execution of stop and wait, or the stop and wait operation in this case. So we look at the utilization or the operation of stop and wait, right? So at time t naught, remember this is same diagram जो हमने पहले भी किया था अपना, ये sender and receiver, and this is the timer increasing downwards, right? At time t naught, the first bit is transferred, and this is time when we are done transmitting the last bit. Okay, and this is time when we started receiving the first bit, and this is the time when we receive the last bit from this packet, right? And then this is the acknowledgement generated by this receiver, and uh, this is the time taken uh, to transmit a packet and then receive its acknowledgement, known as RTT, right? the time required to send a packet and receive its acknowledgement, right? So this is where we finish transmitting the packet, and this is the time when we received its acknowledgement, and this time is known as the time to send a packet and to receive its acknowledgement is known as RTT. Okay, if you just look at this operation, you can see that most of the time, it's just visual understanding can tell is telling us that the most of the time the link is what the link is free. I'm only sending data for this much amount of time, and then I'm for this much amount of time I'm waiting for what acknowledgement. Because remember, in stop at wait, we send one packet and then we wait for the acknowledgement. Okay.
Yes,
So
sir.
now at this point, the acknowledgement arrives, right? And then we can send the next packet, right? So how much time it is taking? The T is what? RTT plus L over R. This L over R is what?
Transmission delay time.
This time, I mean the time taken to send this data packet having 8,000 bits, right? So ज़रा देखिए इसको. So if I now calculate the utilization of the sender, right? So this is what RTT plus this is the RTT, right? The time that we are waiting to receive an acknowledgement sending the packet after sending the packet. Yes, no, yes, right? So and this is
Yes, sir.
what this is the time for which the channel is utilized, and this is the transmission delay. Yes, no,
Yes, sir. Yes,
yes,
sir.
yes, right. So if I am interested in calculating the utilization, I will divide the amount of time I have taken to transmit the packet, which is this time, okay, L by R, right? And I will divide it by the total time, which is L by R plus
RTT.
RTT. This will give me the fraction of time. I mean, for how much I have been utilizing the channel. So L by R is what? 8 microseconds. Yes, no.
Yes.
So
Yes, sir.
point 0.008 divided by from where
The
we
total time,
yeah,
30
from where
seconds.
did we get this 30?
By adding the RTT and the
RTT ये
and the
देखें
what?
हमने propagation ये देखें right.
Yes, sir. 15 micro, 15 ms into two times.
Yeah, okay, okay, yes, no,
Yes, sir. Yes,
yes,
sir.
right. So now if I do this, look at the utilization of the link is 0.00027. Are you okay with this utilization of the link?
No,
It's
sir.
very less, right?
No, sir.
Yes, it's not. I mean, most of the time, the so the RTT 3.0 protocol performance stinks. I mean, this is not acceptable, right? Because we are wasting the infrastructure underlying channel by not sending or utilizing it most of the time for sending the data. And this is primarily because of what? This is primarily because of
Timer.
stop and wait, right? Where we only send one packet and then we wait for acknowledgement, right? About submission, right? So if I really want to improve the performance of or utilization of the link in RTD 3.0, I need to add more. I need to uh, add more packets in flight, right? I should, increase its performance by sending more packets without waiting for an acknowledgement, right? So what is happening in the previously? We send one packet and then we do not send the next packet until we receive its acknowledgement. Yes, no? Yes. This is stop and wait. This is how stop and wait works. But if we talk about a pipeline protocol where we can inject more, there can be multiple packets allowed in flight, So I have sent packet number one, then many other packets are on the way as well, and without waiting for acknowledgement, right? So without waiting for an acknowledgement, I can send n number of packets, where this n depends upon a lot of factors. Okay,